So before we get to that, let me just reiterate that last week I talked about how a lot of situations trying to use Newton's laws and then kinematics and tying them together with the acceleration that's common to both of those can be pretty tedious and pretty difficult. Sometimes, without pretty hardcore calculus, impossible. Very often, those types of situations can be approached from an energy standpoint, and that approach can be much
Good morning.
easier.
It's time again for our drawing of our 12 days of Christmas. We're down to 5.
Okay,
5
let's
days
keep
left.
it. Come on.
Our
Come
winner
on, let's
today
do
is Miss Abby Keaton. Come on down. You are today's winner. There's 4 more to go. 4 more to go.
Okay. So, a lot of students then wonder, well, when can I use conservation of energy? Well, there's kind of an easy, conservation of mechanical energy, I should say. There's kind of an easy way of recognizing when a situation can be, when you can apply conservation of mechanical energy to a situation. And that is when an object or a system of objects is changing velocity and, not or, and, underline, elevation simultaneously. So like it's an object rolling downhill or rolling uphill, sliding downhill. Not just that though, it could be a pendulum. When I take a pendulum, and let's just call this the 0 point for gravitational potential energy. If I move it to the side, he's now got some height above that point, so he's got gravitational potential energy. As it swings down, it converts that gravitational to kinetic. And then it converts that kinetic back to gravitational. And then it just does that over and over and over again. Right? Make sense? And so, pendulums, I can definitely analyze. We couldn't use Newton's laws of motion to answer the problem, how fast is the pendulum moving at the bottom of its swing? I mean, we could, but not with what we know in this class, but we can definitely use conservation of energy to attack this problem. And so this definitely applies. Object is changing velocity and elevation simultaneously. So I can use the conservation of mechanical energy, which says the initial mechanical energy in the system, ME naught, equals the final mechanical energy in the system, ME. And at this point, we have 2 types of energy, 2 types of mechanical energy. We got gravitational potential, and we got linear kinetic. By the end of the year, we'll have 4. We'll have, actually kind of 5 maybe. We'll have, we'll add spring potential energy, which is like this guy. I store spring energy by stretching the spring, and then it converts to kinetic after I let go. That's the same situation as like a bowstring. You pull back on a bowstring, and you're storing elastic potential energy. And so we'll study that a little later this year. And we'll also do spinny kinetic energy, rotational kinetic energy. But as of now, we just have 2. So the initial mechanical energy can be divided into 2 forms. The initial gravitational, U go, and the initial kinetic, K naught. And the final mechanical energy can also be divided into 2 forms, gravitational potential and kinetic. Now, anytime you write this statement, which again is just the statement of conservation of energy, be sure that before you go on to the next step where you actually plug in the equations or the expressions for these guys, see if any of them are going to be 0. If the object's at the lowest point where you've defined the 0 point to be 0, then it doesn't have gravitational potential and you can cross it out. If you know an object is not moving at the beginning or at the end, then you can cross out the kinetic, because with kinetic energy you must have velocity. As a reminder, what's on the formula sheet, what we're going to plug in here, this is how it's written. Gravitational potential energy, it's actually written as change in gravitational potential energy, is mg times delta y. Remember, it's not gravitational potential energies generally that are important, it's the change in, and that's why we have initial and final here, right? If I subtract UG naught, then I have final minus initial, So usually when we're plugging into this, though, we just use the gravitational potential energy at a certain height is simply mg times the vertical position at that height. And a lot of books a lot of classes in pre-AP and on level, we just write that as MGH. But in big kid physics, it makes a little more sense to talk about vertical positions as opposed to just height. Okay, it's more It's more rigorous that way. But you want to think of it as height because it's just the height above the ground. And so you could say that, and then I will be using this though. I will be using that whenever I plug it into this equation. And then our kinetic energy equation is 1/2 mv squared.
Wait, so Mr. Graham, if an object's going down, if it's still a positive gravitational, what you call it?
If it's going down, delta U would be negative. But U itself is just what's the gravitational potential energy when it's at a certain location, regardless of what it's doing.
Okay.
Yeah. They make it a little confusing on the formula sheet. Probably a little more confusing than it needs to be at this level. But it is true. It is their equation is true. Just understand that I could manipulate this equation to have final gravitational minus initial gravitational by subtracting this term from both sides, right? Which would be delta U. But then if I plugged in this mgy minus mgy naught, then I would end up just right back where I started, and it would still work. That's why I like pointing out, even though that's what's on the formula sheet, you can think of the gravitational potential energy of any object as just mg times the height. Why is it, by the way, mg times the height? Take AP Physics C next year and we'll actually prove that. We'll actually use the work energy theorem to prove that this is true, or the definition of work to prove that that is true. Okay. So, all that being said, remember each one, we got 4 terms here that gets an equation, right? Each one gets an equation. That's why it helps to notice at this point, before you start moving on, are any of those going to be 0? Well, I'm going to release the pendulum. I'm going to pull it to the side and release it, so its initial velocity is going to be 0. So it has no initial kinetic energy. And then it's going to end up down here with the final velocity, but it's going to be at 0 height. So I know that the final gravitational potential energy is just going to be 0. That simplifies our life a little more. Because now we just have the initial gravitational is going to equal the final kinetic. And that should make sense, right? You do some work to pull an object up, so you do the work that stores the energy. When you let go, that energy then gets, the potential energy then gets converted to kinetic energy. And then we can plug in these values. Mg, or those expressions. Mg times the initial height, why not, is equal to 1/2 times the mass times the speed at the bottom of the swing squared. I forgot to label the lengths of my pendulum. So this length right here, length L. And then everybody brought mass to the party. So I get G y naught equals 1/2 velocity at the bottom squared. The question here, is determine what the speed is at the bottom. Determine an expression for the speed of the object at the bottom. Then I multiply both sides by 2. Numerator 2, denominator 2. 2g times the initial height equals final velocity squared. Square root both sides. And then get the final velocity is equal to the square root of 2g times y naught. What if the problem said this, though? What if the problem said determine v at the bottom in terms of L, I think just L, in terms of L and fundamental constants. Sorry, L theta and fundamental constants. Get used to seeing that, and fundamental constants. That just means G at this point. That means I can't have y naught in my answer, right? And so the reason I picked this example is because not only with just conservation of energy, there's a lot of situations where you got to figure out a distance in terms of a triangle, in terms of the geometry of some triangle associated with the situation. So what I can do here is realize that this is the length of the pendulum. This is also the length of the pendulum, right? And then I can make a right triangle here by doing this. And I can use that right triangle to figure out what this distance is. And let's just call it some variable. Let's call it x. And then I can realize that whatever the initial height is, plus that distance, which I can determine, equals the length of the pendulum, which can be in our answer. Does that make sense? If I take y naught and put it over here, let me erase this guy. Let's just look at the geometry for now. This right here is y naught. Putting it here should make it obvious. Y naught plus this distance x should equal the length of the pendulum. That's just geometry. And well, I can determine x in terms of theta and L using SOHCAHTOA trigonometry. What trig function involves this angle, this side, and the length? Cosine. So the cosine of the angle is going to be equal to the adjacent side, which we've called x. You can call whatever you want, though, over the length L. Multiply both sides by L, and I get that that length is equal to L times cosine theta. I can actually label this now with L cosine theta if I wanted to. Well, I know that L cosine theta plus y naught must then equal L. So if I write that, L cosine theta plus the initial height y naught equals the length of the pendulum. And then I just solve that for y. I can now replace y naught in my answer with an expression in terms of L and theta. So I just subtract L cosine theta from both sides. I get the initial height is L minus L cosine theta. And I'm sure your pre-cal teacher would like you to, and this is how your most physics teachers will want you to as well. Usually whenever you see this expression, because again, it pops up all the time. Some distance minus some distance times the cosine of the angle. Right? You see that all the time in physics. I can factor out an L. And I end up with 1 minus cosine theta in the parentheses. You don't have to do that, but it's just good practice to factor things out once you see that they have two terms with a common factor. And so now I can replace y naught with that expression. So I get that the speed at the bottom will be the square root of 2g times L times 1 minus cosine theta. If we had numbers, we don't, but if we did, we could throw those in there and determine what that speed would be based on just the angle and the length of the pendulum itself. So a little bit of geometry there, a little SOHCAHTOA geometry, right angle trigonometry, right triangle trigonometry. Okay. But again, same starting point. Initial mechanical equals final mechanical energy. Doing this problem with Newton's laws, very difficult. Because the acceleration is constantly changing. The linear acceleration, it has its biggest value when it's up here, but it has a smaller value here. Because the acceleration is constantly changing, Newton's second law, the algebraic form of Newton's second law will not work. So we couldn't even do this with what we know. We couldn't do this problem without energy considerations. Sound good? Can I erase that and move on to the roller coaster? Cool. All right, so this one is the multi-part FRQ that's on your set of notes that I handed out last week. So if you want to pull that out, go ahead. I will read it though, so we'll be on the same page if you don't have those on you. A roller coaster ride in an amusement park lifts a car of mass 700 kilograms, so that's this guy, 700 kilograms, to a point A at a height of 90 meters. So my initial y, 90 meters, above the lowest point on the track as shown above. Define the lowest point as ground level is the 0 point. That's where gravitational potential energy is 0. The car starts from rest at point A, rolls with negligible friction down the incline, and follows the track around a loop of radius r. Imagine that's a circle. Didn't draw that well. Point B, the highest point on the loop, is at a height of 50 meters. So at one point, that'll be our final height, 50 meters, above the lowest point on the track. Now part A, you shouldn't even need to know physics to answer part A. You shouldn't even really need to have ridden a roller coaster, but you'll definitely know if you've ridden a roller coaster. Indicate on the figure the point P at which the maximum speed of the car is attained. Where is your roller coaster traveling the fastest?
On the bottom.
At the bottom of the first drop. It's all labeled out with point P. Obvious. Notice all of the gravitational potential at point A has become kinetic at point P. No more gravitational potential, so all of the energy is kinetic. Okay. And then as soon as you start moving up to go over the first tail or through the first loop, you start losing kinetic, you start gaining back potential energy. Right? Notice, jumping ahead. Now part B says, what is the value V max of that maximum speed? Well, I can, again, Newton's laws, not going to help us here, unless we know some, and I'd probably have trouble. I could probably do this with Newton's laws, but it would be a nightmare. It would be a nightmare involving pretty hard calculus, because you have the direction, the slope is constantly changing. The slope of the ride itself, because the slope changes, the net force is constantly going to change, the acceleration is constantly going to change. So figuring out the change in velocity based on all that, incredibly difficult to do using just Newton's laws and kinematics. But what I can do is just use energy, because as you'll see, you have an object changing elevation and changing velocity simultaneously. And when an object or system changes velocity and elevation simultaneously, chances are you can use conservation of energy. So for part B, I'm looking for the speed V max, which happens at point P. I can just use conservation of energy. And as you'll see, this will look very similar to what we just did with the pendulum. But I'm going to write every step. Some students can skip maybe this first step, but I like writing every step to focus my thoughts, to make sure I know what I'm doing. So if the energy is conserved, if there's no non-conservative forces like friction acting, which there's not, then the initial mechanical energy must equal the final mechanical energy. As an aside, an equivalent statement here, if ME naught equals ME, this is just another way to think about whether energy is conserved or not, mechanical energy is conserved. If I subtract the initial mechanical energy from both sides, I get 0 on the left side. What's final minus initial mechanical energy? What's another way of writing that? Change it. Excellent. So if the change in mechanical energy of an object is equal to 0, then mechanical energy is conserved. So that's another way of looking at whether conservative forces are acting. If only conservative forces are acting, then this will be true. And that's like gravity and electromagnetic and what we're talking about. Right now it's just gravity. If non-conservative forces are acting, then the change in mechanical energy will not be 0. And we'll actually see our first example of that at the end of this problem. But realize that this statement is the same as that statement. That's, again, why I like writing the statement first. It focuses my thoughts and makes sure that I know that I'm writing a statement that indicates that conservation of mechanical energy is a thing in this situation. Then I just expand it out again. Initial gravitational plus initial kinetic equals final gravitational plus final kinetic. At this stage in the game, I always ask myself, are any of those 0? Well, it says I start from rest at the top, so my initial kinetic is 0. At the bottom, I'm at the 0 point, so my final gravitational potential energy is 0, just like it was with the pendulum. As you'll see, we get the same equation. We literally get the same equation. Initial gravitational potential, mg times the initial height. But now we don't have to do any right triangle trigonometry stuff because it's not a pendulum. So mg times the initial height is going to equal the final kinetic, which is 1/2 mass times our maximum speed squared. Just like with the pendulum, everyone brought mass to the party. So I get g y naught equals 1/2 times that maximum velocity squared. I multiply both sides by 2. Numerator 2, denominator 2. And I get 2 g y naught equals that maximum speed squared. And then just square root both sides. And I get that the maximum speed is equal to the square root of 2g times y naught. And then we just plug that in. So our maximum speed, the physics is done, right? I like saying that. The physics is done at this point. The rest is literally just arithmetic and plugging stuff in the calculator. This is the physics. That's the answer to the physics. Now we're just plugging and chugging. So if this was a real FRQ, most of the points come from this, and then maybe 1 point for the actual numerical answer. If there even is a numerical answer, a lot of these problems, it's just answer in terms of, the given values. So square root of 2 times 9.8 times the initial height of 90 meters. And obviously, it's easy to see doing that in your head that that's 42 meters per second. I'm just kidding. I did that last period and I remembered it. Because 42. You guys know the significance of the number 42?
It's the secret to the life universe.
Gavin knows.
Wait, what?
What is it? The secret to life, the universe, and
Life, universe, and everything.
It's a literary reference. Hitchhiker's Guide to the Galaxy. Good book. Very weird, though. Very weird. All right, so, again, this problem, with our knowledge, impossible without energy. Got to use energy. But you will end up with the same answer. If you did the really hardcore physics, the hardcore Newtonian mechanics to come up with the same answer, or to come up with the answer to this question, you get the same answer, and you have reams more work to do. Okay. Okay. We good with that one? Feel all right? Okay, the next one, calculate the speed VB of the car at point B. So now we want to know how fast that car is moving at point B. We call that VB as our question mark. Now you should, when you see this problem, your brain should say, there's a loop there. So I should probably be thinking about vertical circular motion. And like right when you look at it. We are in the realm now where free response questions and multiple choice questions will not just be dealing with what we're currently